finish getting set up here. Thank you. Oh, that's the opposite direction. Which one? All off? All off. I have to hold it down. All right, thanks a lot. So my name's Brant Robertson. I'm a professor here at UC Santa Cruz, and today I'm going to be telling you about the production of cold gas and galactic outflows. This is work that has been conducted with primarily by my former student, Evan Schneider. She's now a Hubble Fellow at the department in Princeton. And some of this work was also done with Todd Thompson, who was at Ohio State. So it's a rare occasion, but this time I agree with Avishai. Supernova explosions are among the most important mechanisms, physical mechanisms in setting the properties of galaxies. It's something that definitely regulates the star formation in galaxies, and it also has large-scale observable phenomenon. Here is the classic picture of M82, where you can see evidence of the supernova explosions driving a hot wind that then has multi-phase characteristics that you see here in H alpha. So, you know, I think that we're all in agreement that this is something that's necessary for us to understand galaxy formation. It's a feature of all of the simulations, I believe, that have been discussed here at this conference. I think, though, that we need to pull away a little bit and try to understand some of the detailed characteristics of what's going on in the outflows, because the outflows really are the observational evidence of this large-scale mass loss that occurs owing to the supernova. And so a lot of the talk today is going to be about trying to do controlled simulations of galactic scale winds in global disk simulations with extremely high resolution. And what high resolution means to me is different than what it means to other people. We'll go into that in some detail as well. So the first thing I wanted to do is to provide some context with the observations. These are observations that really have inspired me over the years, and some of them I learned about here at Santa Cruz, and so it's great to be able to talk about them. We know that there's cool, fast outflows from galaxies. They're ubiquitous, and you see this as magnesium, for instance, magnesium absorption seen in the spectra of galaxies at redshift 1. This is in Cosmos. This is deep observations, the Deep Galaxy Survey collaboration led by Sandy and others here, and David. And then in Chuck Steidel's work in a variety of absorption signatures here. And there's cool gas outflowing from these galaxies at velocities that can reach up to 1,000 kilometers a second. This is a really dramatic velocity for cold gas to be moving. Okay. So this already, you know, tells you that there's cold material that's moving very quickly from the centers of galaxies. But of course, it also raises the idea of how do you get that gas leaving the galaxy and moving so quickly. Okay, and so this is something that many of the simulations that you've been people have been showing do claim to reproduce some of these observations. And, you know, I'm interested in why this happens or how it actually happens in some detail. It's also the case that cool gas litters galactic halos. This is one of the big results. Over the last few years, the COS spectrograph on Hubble has made this possible to look for, in local galaxies, fairly local galaxies, the absorption, say, from silicon. This is from Borthacker et al. You can see the equivalent width of silicon around galaxies as a function of radius around the galaxies. It's declining, but there does seem to be evidence for this cold material all the way out to the virial radius or beyond. Okay? And it's seen in galaxies of different types. You see it both in star-forming galaxies at the left and quiescent galaxies at the right. Okay, so it's something that's, I said, ubiquitous in star-forming galaxies, but also it's indicative of a phase of galaxy evolution that somehow takes cold material and places it in the halo or forms it in the halo. We don't know which one. So I think this has generated a lot of discussion. I've been to conferences where we literally talked about Jess Work's figure that's similar to this for 8 hours straight in a conference. That was the only thing we talked about. And so, you know, I won't spend that much time, but maybe it'll feel that way by the end of the talk. So why did I say that it's It's one of the very interesting things about this is you might say, well, let me just take that cold material and let me throw it out of the galaxy. I'm going to sit there and I'm going to push on it with extremely hot supernova. And the problem with this is that those cold clouds, they get destroyed pretty easily. So here, this is simulation work that Evan and I did for part of her thesis, where you just take a turbulent cold cloud and you hit it with a hot supernova wind, and you destroy the cloud. So basically, shearing instabilities can just rip apart the cloud and shred it. There's some debate about how small the cloudlets can get at this point in time. You might be able to have some magnetic fields that provide some support to the gas. But the problem is, as you can see, the spectrum of the surface area of these little cloudlets, you can tell it's peaked at very, very small surface areas. So this is like pushing on needles with a hot wind. It's very difficult to take this cold material and accelerate it. As you can see from the simulation, the hot wind is moving much, much faster than the cold material here. So how are you going to take this? This cold material only gets up to 100 kilometers a second when it's blown on in this way. So this is not an explanation in itself. This entrainment of the cold material and the acceleration of the cold material does not seem to be a very auspicious way of going about getting the cold absorbers at a very large velocity. That being said, it seems as though galaxies are able to put this cold material into the surrounding regions around galaxies. So here we have local starburst galaxies. Everyone talks about M82, but there's at least 2 others. I have triplets, so I have to do everything in 3s. You have M82, and you can see, this is, well, mostly X-rays here, but you can see the multiphase structure of NGC 3079. You can see this hot N2 plus H alpha material and filaments. You can see similar stuff in N2 around NGC 1428. So I'd like to use hydrodynamical simulations to actually understand the physics of these multiphase outflows. And that's actually quite a tall business in itself, and so it requires some effort. So how are we going to do this? Well, we're using a code called Cholla. Cholla is the code that Evan wrote for her thesis. I'm going to talk about a little bit in detail, maybe more detail than some people want, but this is the only talk on Cholla. There have been 20 talks on fire, so people, you get to hear about our stuff now in some detail. So what's neat about Cholla is that Cholla runs on GPUs. Now, many people, when they say, oh, I use GPUs in my simulations, really what they're saying is, I farm out a little bit of the work to a GPU now and again. We do all of the hydrodynamics on the GPU. Okay, from start to finish. All we do on the CPU is the communication, at least right now. Okay, so this really is a GPU native code that makes it different than many of the codes that you've been hearing about. Another feature of this code is that the code is a static mesh code. It is not AMR. Okay, you might say, well, that makes it useless. Many people have told me that. But what's nice about this code is that, as you'll see, the performance of the code is really stellar. And this allows us, if we can run on many GPUs, to simulate extremely large volumes and large numbers of cells. The simulation I showed you of the cloud being destroyed had over 1 billion cells in that calculation. Whereas people, the high resolution simulations people are talking about here, the highest zoom simulations had 250 million particles for a single galaxy. We're using 1 billion on a single cloud, and we use tens of billions on a single galaxy later. It has all of the fancy hydro that people have come to expect. And there's some fancy tricks that Evan and I have worked out for radiative cooling, things that make use of special memory on the GPU, but I won't go into too much detail. What's nice about this is that some of the world's fastest supercomputers, the vast majority of their power is in GPUs. So this is Titan. This is the system that we ran most of the simulations I'll show you today on. Titan used to be the world's fastest supercomputer. Now it's Summit. We know that Cholla worked extraordinarily well on Summit. It's super linear speed up given the increase of the power of the GPUs, because the bandwidth between the CPUs and the GPUs on Summit is better than former systems. This is the world's fastest supercomputer, and we've been lucky to do some initial tests. Hopefully we'll get some time very soon on this system. So excellent scaling. So why does this matter? If I'm interested in simulating very large volumes with large numbers of cells, I want to know whether if I can throw more GPUs at the problem, can I run a bigger simulation? And the answer is that indeed we can. In fact, Cholla shows basically perfect weak scaling out as far as we've tested it. We've tested it to 16,000 GPUs. This is a 500 billion cell test calculation that we've done here. And you can see we can do a simulation on 16,000 GPUs in the same amount of time if you keep the work per GPU the same as basically 1 or 2 GPUs. So that's pretty phenomenal. That means we can run extremely large simulations like I'm going to show you. I also wanted to raise one issue about performance. So, Cholla is a static grid code, but one of the nice things about static grid codes is the ability to simulate symmetrical problems to machine accuracy. People emphasized other machine accuracy precision issues earlier. One of the things that you'll realize is in this kind of implosion problem, you'll see that a jet starts to develop along the y=x axis of the simulation. If you don't preserve symmetry in this calculation, you don't develop the jet. So there are actually cases where if you have noise in your reconstruction, or if you're sampling the density field in a way that is not homogeneous, you actually will not have the same phenomenology as you do when you have a symmetrical calculation, when you expect that symmetry to persist. There are 56 billion cell updates, and this is symmetric to machine precision, which is pretty good. We also can run 40 million cell updates per second per GPU, which is a lot. Okay, so what am I going to be talking about in the time? I have no idea how much time I have. 10 minutes, that's good. So I'm going to be talking about seagulls. These acronyms get worse and worse as time goes on. And so what we're doing is we're simulating galactic disks. We're simulating the entire disk, okay, an M82-like galaxy. And we're simulating at a volume that's 10 by 10 kiloparsecs by 20 kiloparsecs, but we simulate it with about 18 billion cells, and we have the same resolution everywhere. Okay, so we have 5 parsec resolution. That may sound lousy compared to 0.1 parsecs that you heard earlier, but we have that everywhere. The volume filling resolution is the same everywhere. Other simulations that do Lagrangian schemes or pseudo-Lagrangian schemes, their volume filling resolution is orders of magnitude worse than their best resolution by definition. Okay, so it's a very different kind of calculation, and it's useful for understanding the multi-phase development of a hot phase that is inherently quite low density and quite hot. Okay, there are many people who have done patch simulations trying to understand galactic outflows by simulating small patches, and the reason for that is that it's very difficult to do this kind of calculation. We can only do these global disk simulations because Cholla is an amazing code that Evan has engineered. Okay, so I'm going to run you through a few of the features. So we're just simulating an isothermal disk. It's in hydrostatic equilibrium with a static potential. And we're simulating a galaxy like M82. We can vary the resolution. The highest resolution has about 5 parsecs everywhere in the simulation. And then we can change the feedback prescription. Okay, so we're not simulating star formation, we're simulating the feedback. So what we do is we input energy and momentum, basically mass and energy at the same time, in some volume. We can pick a very centrally concentrated starburst, we can distribute it into multiple clusters, and then we can see what the resulting effect is on the outflow. And we can do this for adiabatic simulations, we can do this for simulations with cooling, we can tell what the difference is and look at some of the physical features in some detail. Also, because these simulations are expensive, for every simulation we have 2 mass loading states. We have a high mass loading and a low mass loading state. This changes the effective eta that you might say, or some people call it beta, the mass loading, and also the energy loading. We do this so that we can get more than one simulation out of a single run. Okay. As you'll see, equilibrium is reached basically in an advection time scale of the wind, so it doesn't matter if we do this kind of scheme. It just helps us get more than one simulation out at a time. So this is an adiabatic simulation with a nuclear supernova cluster at the center. This is in some ways very similar to what you might know as the Chevalier and Clegg model, which I'll show you the results of in a second. And so this is actually just kind of a baseline. What happens when you have no cooling and you put a bunch of energy and momentum into the center of a galaxy? What's interesting though, because of the presence of the disk, you can see that we drive a lot of turbulence. So this is the interaction with the wind in the disk material. This causes some density fluctuations to appear in the hot gas. Okay, I'm showing density and temperature. I'll show a lot of panels like this. And this is just slices through the center to show you kind of the development of the wind, which is kind of biconical in this way. Sandy, I'm going to have to save it for the end. We have too little time. I'm sorry. Okay, so this is what, if you just go along the z-axis, what the density, temperature, velocity of the wind looks like. You can see the wind is driven as a hot wind, reaches about 1,000 kilometers a second. The reason for that is that the Chevalier-Clegg model, for the amount of energy that we're inputting as a function of time, this is the solution, the white analytical solution, but there's gravity in the simulation. That slows the wind down a little bit. Okay, so that's basically the only difference from the classic Chevalier-Clegg model, which doesn't have gravity. So you might say, why'd you spend 100,000 node hours to verify Chevalier-Clegg? And the point is that now we're going to turn on radiative cooling and make the feedback more sophisticated. So what should happen in radiative winds? Well, that's an interesting question, and that's something that Todd has worked on. And actually what Todd predicted was basically you have something like Chevalier-Clegg, but depending on the density in the wind, you can predict where the gas should start cooling. So that should set up a cooling radius, and then the wind should decelerate, and then eventually there's some other stuff that happens as you're interacting with the CGM. We don't model some of the stuff out here, but we do have something to say about this. So this is now the same model allowing for radiative cooling with heating at the very center of the galaxy. And initially we have a high mass loading state, and you can see that the wind cools out. And actually, as I'll show you, this is the radius that Todd's model predicts the gas should cool. And then as time progresses, and it's going too slowly for me here, as we go into a low state, you can see that the density of the wind goes down, the cooling radius moves out, and it moves out exactly in the way that you would expect. And that's why the temperature evolution in this model looks the way that it does. Todd's model predicts this exactly. Of course, this is very idealized. I'll skip this. So you might say, what happens instead of just having a nuclear blow dryer at the center of the galaxy? You put in a bunch of little blow dryers that are like clustered supernova. And this is what it looks like. You can see that the structure in the wind is much, much more complicated. It's cooling out of the hot wind. There's wind, cold material that's moving very fast that's cooling out of the hot wind. Some of the disk material is entrained. This has radiative cooling in it. And you can also see that these explosions interact with one another, and that drives ripples in the hot phase as well. And this makes sense because it's basically like having little Chevalier-Clegg bombs going off at the center of this galaxy. They interact. That causes these shell-like features that you see. Okay. So the multi-phase structure of this wind is quite complicated. It depends very strongly on how mass-loaded the wind is. So if the wind is very mass-loaded, then it can cool out on large scales. If it's not very mass-loaded, then the cooling happens on quite small scales. And this also has to do with the entrainment on small scales. So if you have a very high mass loading state, then you can entrain more disk material and push it out. And so this causes a higher density wind, and then the wind cools out even more quickly than you would otherwise expect. I'll skip this. This is the difference between the high and low mass loading state. The low mass loading state is a lot like what we expect for M82. And so you can see the amount of debris and the column density distribution, the ionization structure of this wind will be different. And that's because the overall cooling time scale of this wind and its density structure is different based on what this mass loading is. Okay, and I'll skip that too. We can also compare with X-ray observations. This just tells us that the hot wind is realistic. Okay, so now we need to look at the cool wind. That's something that Evan is looking at. You may wonder, how is this multi-phase structure generated? So here we can do the simulations removing the disk entirely. Okay, so this is the same simulation with all the same little supernova going off, but now removing the disk. Okay, so you can see that the multi-phase structure of this is quite different. It's not nearly as clumpy. If I put the disk back in, you can see that you generate structure in this multi-phase wind through the interaction with the disk, and that's quite important. So one of the things now that we're trying to do is to improve the feedback prescription. So we're gaining in complexity. Eventually, we're going to have a full model of the ISM and driving supernova based on calculations like what Vadim was talking about. But one of the things we need to do is to understand whether the mass loading on small scales is realistic for a cluster of supernova going off. So one of the things Evan's doing with Eve Oestreicher at Princeton is she's doing a series of supernova explosions and in an interstellar medium. and then looking at what the mass loading is as the supernova breaks out of a certain scale. Then what we can do is we can simulate that scale as our cluster of supernova and input the results from this simulation into the larger simulations. And that's something we're still working on here. So now we've changed up the supernova model to actually take into account these small scale simulations that tell us how, if we have a certain number of supernova, how the outflow, how efficient should be. And as you can see, the mass loading definitely differs in this simulation. Unfortunately, I hit back, but just a moment. And you'll see that the large-scale cooling is significantly different. And that's because in this kind of simulation, there's less entrainment of the disk material. Okay, so the multi-phase structure of the outflow is affected by the way in which the supernova are clustered and how much mass loading they have as a function of time. Unfortunately, I've run out of time, so I'll just skip ahead to my conclusions, and I'll take any questions you may have. Thanks.
Yes, Suzanne can come to set up. Yeah.
So it's time dependent. Okay, so basically after the breakout occurs, for the first 100 kiloyears or so after that, basically the mass loading is quite high because you're evacuating the ISM that's nearby, and then it drops down to a lower state. I'll have to give you the numbers, they're written down. Yeah.
I thought there was evidence from the winds that we see that the cold material is on a cone.
Yeah.
Do you see that?
So we do see some evidence for biconical outflow. You may have seen the first picture. But I do have to say that it depends somewhat on what the structure of the disk is, because the disk does help to collimate the outflow. As you saw when I removed the disk, you got a spherical outflow. That makes some sense. And so I'm not prepared to say that we get that exactly right, because it has to do with the structure of a disk that really, we're simulating with exquisite resolution, but we're ignoring basically because we're treating it as an isothermal structure to start. Any other questions? Yeah. Yeah, so there's definitely cold material, but the wind is definitely, the thermal energy in the wind is much, much hotter than the sink of cooling out the material, at least in these simulations. Remember, we don't have the large-scale inflow of gas. We're only simulating a very small radius, and so that could be a radially dependent statement. Once the wind gets to be very diffuse, but of course its cooling time scale is longer, and so that, yeah, it's competition on large scales.
We have to move on. So
okay,
thanks
right,
again,
thanks a lot.
Brant.